Okay, so hello to everybody. Sorry we had some technical problems. I hope you are still with us and still connected for the public lecture within the European Strong 2020 project. And I'm here together with Charlotte van Hulse, and we are very eager to start our lecture. I was talking for kind of 5 minutes, but I didn't know I'm not connecting. Anyway, so welcome to our public lecture. Let me introduce you the lecture of today together with some elements of our European project. I'm the coordinator of the dissemination and communication activities within the Strong 2020 project. And today's speaker is Charlotte van Hulse, who will bring us in the heart of the nucleon. And we will see later on that this is a very, very fascinating, not yet solved issue. However, before getting there, let me tell you some few words about our project, Strong 2020, for which you have here the link if you want to go and see something more. Our project is dealing with the study of the strong interaction at the frontier of the knowledge and has received funding from the European Union's Horizon 2020 Research and Innovation Program. The project is pretty big. It puts together 46 participants institutions from 14 European member states, but we also have participants from other countries, not necessarily European, involving altogether 36 countries. And it involves also more than 2,000 researchers who are working in trying to better understand the strong interaction. I want also to tell you that we are not only doing fundamental research, but by doing so, we are also developing tools for this research, which are finding applications for society. So we are also enhancing the innovation potential in applied research. And it also financed access to world class experimental facilities in Europe, which are COSI, MAMI, LNF, ELSA, GSI FAIR, and CERN, and also to your ACT STAR in Trento, which is an institute playing a special role to put together experimentalists and theoreticians. This is a map of our institutions in Europe and of the countries which are involved in this project. And as I was telling you, we have today a special guest, Professor Charlotte van Hulse, who's going to bring us in the heart of the matter. In the heart of the matter, seen like nucleon. And many of us believe that we know what is the nucleon, like the proton or the neutron, which we know are composed of three quarks. In reality, as Charlotte will show us, this might not be whole the story because the structure of the nucleon is still somehow to be understood. And Charlotte, with her broad experience, which has brought her in many experiments which are studying the nucleon, Hermes at DAISY in Hamburg at Germany, in Japan, Bell experiment at Keck, or at CERN with the LHCb and ALICE experiments, and now with future frontier research, which is supposed to be done at AIC, of which Charlotte will tell us something. And if you want to know more about the activities performed within our Strong 2020 project, just connect to our link. I want also to remind you now, Charlotte, I leave place to Charlotte, that if you want to ask questions, just write them in our chat and I'll take care to convey them and to report them at the end of the lecture to Charlotte so she can answer to your curiosities and questions. Please, Charlotte, the floor, it's yours, and it's a pleasure to have you here with us.
Well, thank you very much. Thank you very much, Catalina, for the introduction and for the invitation. I hope you can all see my slides well. So as introduced, I will try to convey how a future electron-ion collider can help us in understanding the internal structure of the nucleon. Now, the maximally available information about the structure of the nucleon is encoded in so-called Wigner distributions, and these Wigner distributions, they give us information about the distribution of quarks and gluons as a function of their longitudinal momentum fraction x with respect to the longitudinal momentum of the nucleon, where here the longitudinal direction coincides with the direction of the probe that we use to investigate the nucleon. These Wigner distributions also tell us something about the distribution of the quarks and gluons as a function of their transverse momentum and as a function of their transverse position inside the nucleon. Now, nearly nothing is known about these Wigner distributions, and these Wigner distributions also do not have a probabilistic interpretation, but if we integrate these Wigner distributions over, for example, transverse position, then we obtain so-called transverse momentum dependent parton distribution functions, or TMD PDFs, or just TMDs. And these do have a probabilistic interpretation, and they tell us what the probability is of finding a parton of a certain flavor as a function of its longitudinal momentum fraction x and as a function of its transverse momentum. Now we can gain information about these TMDs by, for example, looking at semi-inclusive production of hadrons in the interaction of a lepton with a nucleon. And these type of measurements have been performed mostly at fixed target experiments. And from these first measurements, we obtained first those still very model-dependent images about the inner structure of the nucleon. And here you see the distribution of the up quark in transverse momentum space for different values of x. Now, this is for an unpolarized nucleon. If we would, for example, transversely polarize the nucleon, then you see a shift in this distribution to the right for the up quarks and to the left for the down quarks. Now, if we integrate these Wigner distributions over transverse momentum, then we obtain impact parameter dependent PDFs, which again have a probabilistic interpretation. And they tell us what the probabilities of finding a parton as a function of its longitudinal momentum fraction x and as a function of its transverse position inside the nucleon. Now, we do not directly access these impact parameter dependent PDFs in measurements. Instead, what we access are so-called generalized parton distributions, or GPDs, which are linked to these impact parameter dependent PDFs through a Fourier transform. And we can access these GPDs in the study of exclusive processes in electron-proton interaction, where the final state is fully determined, and we create one or maybe two new particles, and in the process, the proton stays intact. So these processes has been also studied at fixed target experiments, and from this we obtain again very model dependent images. And here you see the distribution of quarks in the transverse position space for a large value of x and for a smaller value of x. And there are subtleties in the interpretation of these images, but what you see is that quarks with a larger momentum fraction tend to be located closer to the center of the nucleon, whereas the quarks with a lower momentum fraction expand to further away from the center of the nucleon. Now, this is again for unpolarized nucleons, and if we, for example, would transversely polarize the nucleon, we again see a shift in the distribution to the left for the up quarks and to the right for the down quarks. Now, if we integrate these TMD PDFs over transverse momentum, or we take the generalized parton distribution in a certain kinematic limit, then we obtain the standard PDFs, which just describe the probability of finding a parton as a function of its longitudinal momentum fraction x. And these PDFs have also, well, can be accessed also again in the study of lepton-nucleon interactions, where, for example, we only detect their scattered lepton, or where we, in addition, reconstruct one of the produced hadrons, but now integrating over its transverse momentum. And here you see reflected our current knowledge on these standard PDFs, where you see them drawn as a function of the longitudinal momentum fraction x, and you see that at high values of x were dominated mostly by the U valence quarks inside the proton, and to a lesser extent by the down valence quarks. And when we go lower and lower in x, you see that we get more and more dominated by the C quarks, but most of all by the gluon distribution. So in order to understand all these different facets of the inner structure of the nucleon, we need measurements, because we cannot calculate all these quantities that I discussed and that are indicated here in green. And especially with the building of the EIC, we hope to vastly extend our knowledge on these different aspects of the internal structure of the nucleon. So a new electron-ion collider, or EIC, will be built in the US with data taking foreseen starting from early 2030, and this detector will be located at Brookhaven National Lab on Long Island, close to New York. And there, longitudinally polarized electrons will be brought into collision with longitudinally or transversely polarized protons, and even deuterium and helium, and also with a whole series of unpolarized heavier nuclei ranging up to uranium. For the polarized beam, we expect a 70% polarization, and we will collect data with different beam energies so that we cover a center of mass energy per nucleon ranging from 29 to 141 GeV. So the first detector for the EIC will be located at the interaction point 6 here. And you see that on the drawing, you also have a second interaction region where the aim is to, at a later stage, install the second detector, which is complementary to this first EIC detector. And this first EIC detector is called the electron-proton-ion collider detector, or in short, the EPIC detector. And here you see a drawing of the central barrel of this EPIC detector as currently foreseen. And this detector will be 10 meters long and 5 meters in diameter, with a full coverage in azimuthal angle and with a coverage in a polar angle ranging from 2 to 178 degrees, which corresponds to a coverage in pseudo-rapidity ranging from -4 to +4. And we'll have the electrons coming from the right that will be brought into collision in the center of the detector with the hadrons coming from the left, where the hadron beam defines the forward direction. And after the interaction, we will detect the scattered lepton, which is mostly produced in the forward and the central region, and we'll also detect the newly created particles, which can be produced in the forward, central, or backward region. Now, for the cases where the scattered lepton is scattered under very small angles and actually escapes detection and stays into this beam pipe here that you see drawn in white, further away from the interaction point at more or less 20 and 40 meters, we'll have two detectors which will be able to detect this scattered lepton, which has been scattered on a very small angles. In a similar way, we have a system in the opposite direction. We have a far forward system of detectors for the particles that have been created very close to the beamline, or for example, for the processes where the proton does not break up in the interaction, but instead stays intact and it's scattered under a small angle, as for example, for the exclusive processes. So this far-forward system consists of a so-called B0 system, which itself consists of tracking detectors for the charged particles and a calorimeter for the reconstruction of photons. Then we also have Raman pods, which are inside the beam vacuum and which, for example, could detect this scattered proton from the exclusive processes. And then for the charged particles that escape detection by these Raman pods, but instead are bent out of the beam pipe, we have here off momentum particles. And then we also have a 0-degree calorimeter for the detection of low energetic photons and neutrons. For data acquisition, we will not use any triggers, but we will continuously collect data, though with a very strong zero suppression at the front end electronics, so that we can discard anything that is not of interest. So I'll guide you now through the different detector components of the central barrel of the EPIC detector. So first, for the reconstruction of the tracks of the charged particles, we will make use of the 1.7 Tesla magnetic field and of the tracking detectors, which are indicated here in yellow. Now for the reconstruction of the vertex and the part of the tracking close to the beamline, we will use good resolution silicon detectors. Then as we move further away from the beamline, where we don't need an as good precision and where we also have to cover a large area, we will use, as indicated in blue here, macro pattern gaseous detectors. And then finally, we also have a time of flight detector for particle identification of low momentum particles. And this detector can provide us an additional space point for the reconstruction of the tracks. Now, combining all these detectors, here you see the relative momentum resolution of these reconstructed charged particles as a function of their momentum for the central barrel region and for the backward region. And in the central region, as indicated by the red and black points, you see that we have a good momentum resolution, and that this momentum resolution satisfies what is required for the physics program, as indicated by this dotted line. Now, on the other hand, in the backward region, you see that there, especially for the lower momentum particles, our resolution is not as good. But here we can count on the help of the electromagnetic calorimeter for the reconstruction of scattered lepton, as I will also illustrate towards the end of the presentation. So we'll have electromagnetic calorimeters in the backward, central, and forward region. And in the backward region, we really need a very high precision detector because, for example, if you want to look only at study of inclusive processes where we only detect the scattered lepton, then we have to be able to reduce the background to a very considerable amount. And our main source, our background, will be contamination from pions. So this detector needs to help us to disentangle signals from electrons and pions. In addition, as I already mentioned, this detector will also help us in the reconstruction of the momentum of the scattered lepton. Then in the central region, we will have silicon sensors and combination of LED and scintillating fibers. It will allow us to reconstruct the shower in 3 dimensions. And then in the forward region, well, here mostly very high energetic particles are created. So with the electromagnetic calorimeter, we want to reconstruct these high energetic particles, but at the same time, we also want a good resolution for the lower momentum particles. And in addition, we want that this calorimeter provides us a space point that we need in particle identification. So this results in a detector that will be very finely segmented. Then we also have a series of hadronic calorimeters. Again, in the forward region, we want to reconstruct the high energetic and the lower energetic particles with good resolution. So here we will use a combination of steel and tungsten together with a scintillating material. The calorimeter in the central region will be mostly used for the reconstruction of neutral hadrons. It will not contribute to the reconstruction of the charged particles because in this region we already have a very good tracking resolution. And then in the backward system, we will have a hadronic calorimeter that will mostly serve as a tail catcher of the signal. Then for the identification of the particles, we will mostly use Cherenkov detectors, which are based on the principle that when a particle in a material travels faster than light in that material, the particle will emit a cone of light, and the radius of this cone is related to the velocity of the particle. Since we know its momentum from track reconstruction, we basically know its mass and thus its identity. And by using these detectors, we can distinguish between pions, protons, and kaons, and it also helps us in the identification of electrons. So we will have a Cherenkov detector in the backward region. Then in the central region, we'll have a DIRC, which is also based on detection of Cherenkov light, but where this light is internally reflected and then read out at the end. Such a detector was needed because we have not so much space here in the central region. And then in the forward region, we will have again a Cherenkov detector, but with two radiators, one for the creation of Cherenkov light from lower momentum particles and one for the creation of Cherenkov light from higher momentum particles. And then for the particle identification of low momentum particles, we will also have this detector based on time of flight, as I already mentioned. Okay, so we can study part of the inner structure of the nucleon by, as I already said, looking at processes where we only detect the scattered beam lepton after its interaction with the nucleon. And this interaction with the nucleon can proceed through the exchange of a virtual photon. And here one variable of interest is the photon virtuality, which is the negative of the 4 momentum squared of our virtual photon. And in order for this virtual photon to resolve the inner structure of the nucleon, its virtuality needs to be above 1 GeV squared. The other variable of interest is the Bjorken X variable, which is reconstructed from 4 momenta of the incoming beam proton and the virtual photon. And this variable can at first order be equated to this longitudinal momentum fraction x that appears in the distribution of the standard parton distribution function. So by studying this type of processes, we gain access to the standard gluon PDFs and also to the quark PDFs, but where we somehow average over the different types of quark flavors. Now, if in addition we detect one of the produced hadrons, then we get some handle on the flavor of the quark that interacted with the virtual photon. For example, if we look at positive pion production, well, since this positive pion consists of an up quark and an anti-down quark, and since the proton itself contains 2 U valence quarks and 1 valence down quark, it's quite likely that this U quark here in the pion is one of the valence quarks of the proton that then interacted with the virtual photon, and that combined then with an anti-down quark picked up from the vacuum. So by looking at different types of hadrons, we get a handle on the different flavors of the quark inside the nucleus. The only drawback is that we have an additional function, namely the fragmentation function, which describes the fragmentation or the hadronization from the struck quark to the final state hadron. And this function needs to be determined again from experimental measurements. Now, if in addition we take into account the transverse momentum of our produced hadron, then, as already mentioned, we get access to these TMD PDFs. And also the fragmentation functions acquire a dependence on transverse momentum. And here, the transverse momentum of the hadron is a contribution from the transverse momentum of the struck quark while it was inside the nucleon, and in addition, the transverse momentum that the struck quark acquired in the fragmentation process. Now we can collect data using an unpolarized nucleon. We can also look at data using a longitudinally polarized nucleon and using a transversely polarized nucleon. I also want to mention that these TMD PDFs evolve as a function of Q-square. Also, the standard PDFs evolve as a function of Q-square, but this TMD evolution is different from that of the standard PDFs, more complicated, and actually also needs information from experimental measurements. So here you see the kinematic coverage in terms of Q-square and X-Bjorken as foreseen at the EIC, where here we're interested in Q-square values above 1. And what's very nice about this plot is that you very much see the complementarity between taking data at different center of mass energies. So if we collect data at the highest center of mass energy, you see that we can go down in X to a 10 to the minus 4, whereas if we use the lower center of mass energy, you see that we are mostly covering a higher region in X. And we can probe the internal structure of the nucleon up to values close to 1 of X. So first I'd like to show you the impact of the EIC on determination of the standard spin-independent PDFs. So here, on the left-hand side, you see in red the uncertainty shown by this red band here as a function of X for the valence U quarks, and on the right you see something similar for the gluon distributions. And you see that at low values of X, so it's not very visible, and at high values of X, we at the moment have very large uncertainties. The blue bands indicate the impact of the EIC, and you see that especially for the valence U quarks and for these higher values of X, we'll get a strong reduction in uncertainty. Now, it's very interesting to perform these measurements not only on nucleons, but also on nuclei. If you compare the proton PDFs for protons inside a heavier nucleus to the PDF extracted from a free proton, then you see that the ratio of these PDFs is not constant, but instead can be below or above 1, depending on the region in X that you are probing. And the mechanism behind this behavior is not yet well understood. And so to understand this better, it will be very useful to collect data on nuclear targets, a whole range actually of nuclear targets. And here you see on the right-hand side our present knowledge reflected for the nuclear PDFs of the gluons, the anti-up quark, and the U valence quarks. Our current knowledge is reflected in this cyan band here, and the impact of the EIC is indicated by this blue band. And you see that the EIC will really have a considerable impact on the reduction of the uncertainties for this nuclear PDF. Now, if we collect data using a longitudinally polarized lepton beam and a longitudinally polarized proton beam, then we get access to the helicity structure of the proton, and we can look at the amount of partons that have their spin aligned with the spin of the nucleon minus the amount of partons that have their spin anti-aligned with respect to the spin of the nucleon. And to learn something about the distribution of the gluons, we can just perform measurements where we only detect the scattered lepton, and we look at the amount of events where the spin of the lepton beam and of the proton beam were aligned minus the amount of events where the spin of the lepton and proton beam were anti-aligned. And we can normalize this to the sum of both configurations, and then we can construct an asymmetry. And here you see the coverage as expected from the EIC of measuring this asymmetry as a function of Q square for different values of X Bjorken. And again, what is nice here is that you see the complementarity between the low center of mass energy data taking and data taking at the higher center of mass energy. So nowadays, we can probe values of X down to 0.05, but only with a very limited coverage in Q square. So with the EIC, we will be able to considerably extend this coverage in Q square, and we will be able to probe X Bjorken values down to 10 to the minus 4. Now, the impact of this type of asymmetry measurements at the EIC on the determination of the gluon helicity distribution is shown here as a function of X. So the light blue band here shows the present uncertainty on this helicity distribution, while the dark blue band shows the uncertainty that we will obtain after combining data from the EIC collected at different center of mass energy. And you see that here the EIC will really have a very strong impact. Now, for the determination of the helicity distribution of the quarks, as already mentioned, we can look at processes where, in addition, we detect one of the produced hadrons to get a handle on the flavor of the different types of quarks. And again, we can just construct asymmetries by looking at configurations where the two beams have their spin aligned compared to the situation where they have their spin anti-aligned. And here you see reflected the expected impact of the EIC. So here what you have to look at is at the size of the uncertainties. The absolute value of the y-axis is meaningless. So here you see the coverage of the EIC as a function of X Bjorken, where the different colors reflect different values of Q square. This is an example for production of negative kaons, and this is here for the lower center of mass energy, and this is for the higher center of mass energy. And you see again the complementarity between the two center of mass energies, and you also see that we have a good kinematic coverage with the EIC with reduced uncertainty. So based on these type of uncertainties, the impact that we can expect from the EIC on the determination of the different C-quark helicity distributions is shown here, again as a function of X. So here you see the uncertainty band for the anti-up quark, here for the anti-down quark, and here for the strange quark. And the light blue band here reflects our present knowledge on these helicity distributions, while the darkest blue band reflects the impact of the EIC when we combine only the lowest and the highest center of mass energy together with an intermediate center of mass energy. So what you see is that the EIC will have a considerable impact, and you should actually only consider the region between 10 to the minus 4 and 1, where the EIC will be able to perform measurements. Anything below is just an extra polish. Now, if we in addition take into account the transverse momentum of the hadron and we write down the full cross-section for this semi-inclusive production of hadrons as a function of their transverse momentum, then you see very lengthy expression and you see different azimuthal modulations appearing. And the angles that are of importance here are the angles between the plane formed by the incoming and scattered lepton and the plane formed by the virtual photon and the produced hadron, which is this angle phi here, and the other angle of interest is the angle between the plane formed by the leptons and the spin of the nucleon. And so you see that there are different modulations. Some of them only appear if the beam is longitudinally polarized, the lepton beam. Others appear when the nucleon is longitudinally or transversely polarized. And so what we do is that we perform actually a fit of these angular distributions, and it's the amplitude of these azimuthal modulations that are directly related to combination of these TMD PDFs and this TMD fragmentation function. Now, depending on the polarization of the quark or of the nucleon, we have different types of TMD PDFs. So some of these TMD PDFs survive if we integrate over the transverse momentum of our struck quark, and then we obtain back the spin-independent PDF that we already encountered and the helicity PDF. But now if we do not integrate over transverse momentum, you see that you have a whole series of additional TMD PDFs depending if the quark is unpolarized, longitudinally or transversely polarized, and the nucleon is unpolarized, longitudinally polarized, or transversely polarized. And for example, you can look at the distribution of unpolarized quarks inside a transversely polarized nucleon. Now, each of these TMD PDFs will combine with a certain fragmentation function. And since here we only will consider unpolarized hadrons, we only have the spin-independent fragmentation function describing the fragmentation of an unpolarized quark into an unpolarized nucleon, and the Collins fragmentation, which describes the fragmentation of a transversely polarized quark into an unpolarized hadron. So these different TMD PDFs will combine each with a specific fragmentation function. So here I will, as an example, only show you one modulation, namely the impact of the EIC on the Sievers distribution, where you can expect some similar impact of the EIC on different types of distributions. So for the Sievers function, we look at the distribution of unpolarized quarks inside a transversely polarized nucleon, and we're actually probing the correlation between the transverse momentum of the quark and the transverse spin of the nucleon. And the Sievers TMD PDF will just combine with the spin-independent fragmentation function. Now, for this Sievers TMD PDF to be non-zero, it requires that the quark actually has orbital angular momentum. And to understand this distribution a bit better, here is a cartoon where we look from above. We have here the incoming and scattered lepton, which will interact with one of the quarks inside the nucleon through the exchange of the virtual photon. And here we look at a transversely polarized nucleon where the transverse polarization sticks out of the screen. You also have to know that, so when the quark, which is rotating inside this nucleon, will interact with the photon, it will do this with a bit larger probability when the photon and the quark move towards each other compared to when the quark and the photon move in the same direction. So in this cartoon here, we have our quark rotating counterclockwise, and then it's a bit more likely that it will interact here on top with the virtual photon. The quark will absorb the virtual photon, and then inheriting its momentum will move more or less straight away from the nucleon remnant. But it will also interact with this nucleon remnant, and it's this additional interaction that will cause this quark not to travel in a straight line, but to be bent downwards. If you would have had a quark which rotates with the clock, so in the opposite direction, it would have been a bit more likely that the quark would have interacted here in the bottom with the virtual photon. It would again move away from the remnant of the nucleon, but because of these final state interactions, it will be bent in the upward direction. And here you see an example of a measurement of this Sievert's amplitude. Let's concentrate on the measurement for positive and negative pions as a function of X. This is from the fixed target experiment Hermes. And you see that the amplitude for the positive pion is positive, which at first order we can consider as, especially at high values of X, as a result of the interaction with the virtual photon with a U valence quark inside the nucleon. And then the U valence quark would rotate in the direction as indicated in the cartoon here. For the negative pion, things are a bit more complicated, since the negative pion consists of a down quark and an anti-up quark, and we have down quarks inside the nucleon. At high X, it could be that this pion originates from the interaction of the photon with down valence quarks, but because the cross-section comes weighted with the charge square of the different quarks, there will be also a considerable contribution from scattering of the U quark. So what we then would see here is the effect of the cancellation from up quarks rotating in this direction and down quarks rotating in the other direction. Now, this type of images has been confirmed by a decent extraction of these Sievert's distributions, a bit more sophisticated than the heuristic approach we used here, but it's just to give you an idea of what we can learn about these different azimuthal amplitudes. Now, as I told you also, these TMD PDFs, they evolve as a function of Q-square, and from the different fits, it has been seen that the azimuthal, amplitude seems to decrease as a function of Q-square. So if at the EIC we want to measure our azimuthal modulations over a wide range in Q-square up to large values of Q-square, we really need to be able to extract them with very high precision, namely better than 1%. And what at the moment results from our study that we can achieve as a precision for the determination of these azimuthal modulations is shown here as a function of PT. Again, the absolute value of the y-scale is meaningless, but you should concentrate on the uncertainties where the boxes indicate the systematic uncertainties and the vertical arrow bars indicate the statistical uncertainties. And what you see is that for low values of X and Q-square, and for moderate values of PT, we actually can achieve a good precision for the extraction of these azimuthal asymmetry, better than 1%. Since the extraction of these asymmetries or azimuthal modulations as a function of Q-square is also important, here in the bottom, you see how well we can extract them and over which range as a function of Q-square for different values of X. And you see that in the moderate to small region, we have a large lever arm in Q-square and a good precision. So based on these type of uncertainties, the expected impact of the EIC on the determination of the Sievert's TMD PDFs is shown here. So here you see in orange the uncertainty bands for the present situation as a function of the transverse momentum and for different values of x, here for the up quark and here for the down quark inside the proton. And the gray bands here reflect the uncertainty that we can expect once we will have EIC data. And you see that EIC here will really have a considerable impact, which is very good because one of the key elements of the EIC is actually the measurement or the determination of this transverse momentum dependent PDF. So far I've talked about inclusive and semi-inclusive measurements, and now I'm going to switch over to what we can achieve by studying exclusive production, where we create new particle and where our proton stays intact. So as I said, this gives us access to the distribution of quarks and gluons as a function of their longitudinal momentum fraction and their transverse position through the access to generalized parton distribution. And these generalized parton distributions themselves do not have a probabilistic interpretation. Instead, there are probability amplitude to extract a quark with a certain longitudinal momentum fraction out of the nucleon and then to reabsorb a quark with a different longitudinal momentum fraction in the nucleon. And hereby, this nucleon stays intact but receives a certain momentum transfer, which is encoded in the Mandelstam variable T. Now, depending on the spin state of the parton and of the nucleon, we have access to different types of GPDs with different weight. And the cleanest experimental access to these GPDs is through the production of deeply virtual Compton scattering, where one of the quarks inside the nucleon absorbs the virtual photon, travels a certain distance, and then emits a real photon, after which it returns back to the nucleon, leaving it intact, but with different momentum. And we can access this deeply virtual Compton scattering through the study of hard exclusive production of a real photon in EP interactions. Instead of looking at the exclusive production of a photon, we can also look at the exclusive production of mesons, such as the Rho, Phi, or J-psi mesons. It's a bit more complicated because we need to describe this evolution from quarks into these mesons, and for this description, we again need experimental data. There is a bit more complicated. The big advantage is that this type of processes give us complementary access to the DFCS. Now, in general, since it's an exclusive process, we could reconstruct this momentum transfer to the proton by only looking at the detected scattered lepton and the produced photon or meson. But thanks to our far forward system, we can actually also directly detect this scattered proton. And depending on the center of mass energy, the proton will be detected in these B0 trackers at low center of mass energy, whereas for the higher center of mass energy, we will use the Raman pulse. Here, just to give you an idea, I show you the expected impact of the EIC on the measurement of the differential cross-section as a function of this Mandelstam variable T, where the different colors indicate different values of Q square and X Bjorken here for exclusive photo production, and here the different colors correspond to different values in X Bjorken for the exclusive production of J-psi. The message here is that we have a large coverage for the measurement of our exclusive processes with reduced uncertainties, and this is really, as for the TM, this is really very important, and it's maybe even more crucial for the extraction of the GP. Now, instead of performing our measurements on nucleons, we can also perform measurements on heavier nuclear targets. And there, what can happen is that if we look at cartoon from a nucleus, where we have our nucleus consisting of protons and neutrons themselves consisting of partons, then our virtual photon can interact with the nucleus as a whole, and then in general, the nucleus stays intact, and we speak about coherent production. Now, when we look at coherent production, the scattered nucleus is scattered over a really small angle, smaller than the case when we look at proton production. And in general, this, at least for heavier nuclei, these nuclei are not detected by the far-forward system. So an absence of signal there would correspond to coherent scattering. What also can happen is that one of the photons interacts with one of the nucleons inside the nucleus, and then we speak about incoherent scattering, and then in general the nucleus breaks up. And we can see the products of this breakup in this far-forward system. So this far-forward system gives us a handle on distinguishing coherent and incoherent production. And depending on what we want to do, this is definitely necessary. So because if you look at the cross-section differential in T and as a function of T, then you see that for very low values of T, we're highly dominated by coherent scattering, whereas very fast for higher values of T, we get dominated by this incoherent contribution. Now, both are interesting. So, for example, what we can learn from coherent production is that we could learn something about nuclear GPDs, because at the moment we know nearly nothing about these nuclear GPDs. And if you want to describe these nuclear GPDs in terms of nucleon GPDs, and we can see actually if we have this same type of effect as I described for the nuclear PDFs. And also coherent scattering is really interesting if we want to learn something about the distribution of the gluons. So as I told you, the lower and lower we go in X, the more and more we are dominated by the gluons. But now in this drawing here, you see that this term here is multiplied by a factor of 0.05. If we remove it, you really visually see this steep increase in the amount of gluons inside the nucleon. And the idea is that this comes from the splitting of the nucleons into additional nucleons, the splitting of the gluons into additional gluons, where each time the newly created gluons have a smaller and smaller fractional longitudinal momentum. Now, it's expected that this rise with lower and lower values of X of the gluon distribution cannot go on indefinitely, because then we would violate unitarity. But the idea is that at some point the gluon density would be so high that the gluons would start to recombine. And then this gluon distribution here would start to saturate. So at the moment there are no clear unambiguous experimental signs of this, but if we want to study this, of course, we want to look at a system where we have a very high density of gluons. And you have to know that when your virtual photon interacts at some transverse distance with your nucleon or with the nucleus, it will coherently interact with all the nucleons or gluons, that are located at the same transverse position. So if we're probing a nucleon, we can only interact with all the gluons that are located at this specific transverse position. But if instead we use a heavy nucleus, which consists of several nucleons, then at this transverse interaction point, we will have a much larger amount of gluons with which the photon can interact. So we will be sensitive to much higher gluon density. And this is why it's so interesting to look at heavier nuclei if we want to probe signs of this gluon saturation. Now, also, incoherent production is very interesting, because if we look at coherent production, there we actually are sensitive to the average distribution of our gluons, for example, inside the nucleus. But if we look at incoherent production, then we start to be sensitive to fluctuations of, for example, these gluon distributions. So for now, most of the studies have concentrated on study of coherent production. And here on the left-hand side, you see studies performed for the EPIC detector, where we have simulated coherent production as indicated by this blue continuous line here. And then we've passed this generated distribution to a full simulation of the Monte Carlo. From this, we have tried to reconstruct this coherent signal. And this is here for the exclusive production of J-psi, where we thus reconstruct our scattered lepton and the two decay leptons from the J-psi. And if we reconstruct this coherent contribution, where we reconstruct a scattered lepton using the tracking system, then we get these blue circles here, which, as you can see, do not very well reproduce this generated distribution. If instead we use this very high precision backward electromagnetic calorimeter for the reconstruction of our scattered lepton, then we obtain this lac distribution here. And if we combine both the tracking information and the information from the backward electromagnetic calorimeter, then we obtain this red distribution here. We do lose some events, but you see that at least we somehow managed to reconstruct for the moment part of this coherent structure. So this really shows you this importance of this backward electromagnetic calorimeter. Then also we want to study how well we can suppress our incoherent production, and this is done here for older simulation of the EPIC detector, which was one proposal, namely the Athena, from the Athena collaboration. And here what has been simulated is again this coherent signal, and on top of this incoherent signal, which quickly starts to dominate at higher values of T. And the exercise here was to try to extract the coherent signal and to suppress as much as possible the incoherent using this far-forward system of detectors. And you see that the reconstructed distribution is given here by the blue circles, while the remaining of the incoherent contribution is shown here by the red stars. And you see that actually up to this third diffractive peak, we are able to relatively substantially reduce and suppress the contribution from incoherent background, which is what we need if we want to learn something, for example, about these nuclear GPDs. So I hope that I've shown you that with the EIC, and more in particular with the EPIC detector, we can address various aspects related to the study of the structure of the nucleon and also of nuclei, that especially for the study of inclusive measurements where we detect or reconstruct the scattered lepton. Here, this high resolution backward electromagnetic calorimeter is important. If we want to study the TMD PDFs and learn about the three-dimensional distribution of gluons and quarks as a function of their longitudinal and transverse momentum, then we need to reconstruct hadrons, so we need very good PID detectors. Then if we look at the complementary three-dimensional distribution in terms of longitudinal momentum and transverse position, then we need to look at exclusive measurements. We can do this for studies on the proton, where we can use the far-forward system to really immediately detect this scattered proton. And if we want to perform exclusive measurements on heavier nuclei, then again we can count on this far-forward system, but then rather to suppress, for example, our incoherent background. So, well, if you're enthusiastic about this program, and if you would like to join the efforts for the EIC, you will definitely be more than welcome, because we still want to do many studies and further develop the R&D of the detector. Thank you very much for your attention.
Thank you very much, Charlotte. Now let me ask if there are some questions from people online. So meanwhile, let me ask you something about the time scale. So what would be a time scale to reach these important goals?
So the idea is that we would start data taking like early 2030. So there's a whole setup of timelines which need to be respected, which I do not know by heart, but they're set up such that we reach this goal by beginning of 2030.
And meanwhile, I imagine that there might be some other experiments, at least partially working on this. So which could be the competitors?
Oh, there are no competitors, I would say, because what we have at the moment, so we had this, for this three-dimensional study of the nucleon structure, so we had some pioneering experiments, which were at Hermes, and experiments at Jefferson Lab, and also actually COMPAS, but where we had always a fixed target. We were probing only a certain higher X kinematic region. And now there's the upgrade of Jefferson Lab, which will have really high luminosity, so they can do nice coverage in different kinematic variables, but they will be concentrating on the higher X region. And if you want to go down to this lower X region with good precision, you really need the EIC. I mean, experiments even with the hadron colliders can at some point, like the LHC, can also provide additional information, but if we want high precision and we want all polarization states, that we really need this EIC.
Right. And then a personal question. So what's the part which is more exciting for you in this context?
Oh, okay. So I like these TMD and GPDs very much, and their complementarity. I hope that also with the EIC at some point we can do some studies which are related to this Wigner distribution, because there are some ideas yet. And then just because I don't know so much about it, I like this low X physics with this gluon saturation and so on. So at the moment I find that exciting.
Which is just in the heart of our project. We want to better understand the hadrons and not only their structure, but also how they interact with the rest of the matter. And I think that from your lecture, it's very clear that there is still a long way to go. We believe we know the proton, we believe we know the neutron. And in fact, yeah, so people are looking for dark matter, but we see that as ordinary matter, it poses enormous challenges. Could you comment on this?
Well, I don't know if I will say something meaningful, but yes, I definitely, I completely agree with you. And well, I hope that in my presentation I showed you some aspects, but yes, we don't know the distribution of the partons inside the nucleon in momentum and position space. We don't know the difference between free nucleons and nucleons in nuclear matter. We do not know what happens with the gluon distribution at the very low X. Also, I didn't comment here because I don't have time, but there was also interest of trying to investigate the structure of pions and even of kaons, which we can do at EIC. And this will also be interesting also to understand the different contributions and interactions related to the determination of the mass of the nucleons and of the hadrons. So, well, I don't know, there's a lot to do.
Yeah, it's a lot to do for the matter which we believe to know. So who knows what we will discover, because yeah, one should not take for granted we know as well as we believe we know the things which are. And I think thank you very much for this lecture, because this proves how difficult it's to perform, but also how exciting is to perform studies in this context and going a step forward for understanding the structure in front of our eyes, and also the one of which we are part of. We are made of this, so it's quite interesting. I want to ask if there is anyone who wants to ask question, either to ask them now, or alternatively, if somebody's seeing this lecture later on, you can send us mail. You have the email in the contacts, and we will take care to convey your questions to Charlotte. And I also would like, if Deborah is there, I'd like to ask her to join us. Hello, Deborah. Deborah, it's a wonderful person from Frascati team of persons who are taking care of all our welfare in the context of organizing and undergoing with our public lectures within Strong 2020, whom you almost never see, but behind the scenes, without persons like Deborah, she's not the only one, but she's, there is a whole team here. So I take the chance to thank Deborah for all of them, for giving us this wonderful possibility and instruments to come and reach you wherever you are. So once again, thank you very much, Charlotte. Thank you very much, Deborah. And see you in the next public lecture in probably December. Bye-bye to everybody.
Bye.
Bye.
Thank you.